In this video, we're going to go ahead and discuss variation problems. So we're going to talk about the relationship between one variable and another. For example, if I increase one variable, what happens to the other one? Does it also increase? Or perhaps as one increases, the other decreases? We're going to look into this and observe what happens. Let's look at our first type of variation called direct variation. So direct variation is where one quantity is a constant multiple of another quantity. So when we look at the formula, we'll see that it's y equals k times x. X and y are going to be our variables or our quantities that are changing. K is going to be our constant. And in fact, k will always be constant. Now, the way that the variables are set up is that when one variable increases, the other variable will increase. And then vice versa. If one variable decreases, the other variable decreases. This is the idea of direct variation. And the example I like to use is working. Okay, how much money am I going to make while I'm working? So let's say I make $10 an hour. Well, how much money I make, let's use M for money, is going to be 10 times the number of hours I work, right? Well, 10 is going to be my constant K because it doesn't vary, right? It's always $10 an hour. And you can see what's going to vary is my number of hours and my amount of money. So I would say my money varies directly with the number of hours I work. So you can tell as I increase my hours, my money also increases, and vice versa. As I decrease my hours, my amount of money decreases as well. So got to get those hours in, right? Okay, now let's go ahead and do an example. So the area of a rectangle varies directly with its length. Now, then it goes on to say, if the area is 50 meters squared when the length is 10 meters, find the area when the length is 25 meters. So there's a couple things that I want you to notice in this problem. The first thing is the area of a rectangle varies directly. When you see that varies directly, I want you to stop and go, oh, it's a direct variation problem. As soon as you hear that phrase, varies directly, I want you to stop and say that's a direct variation problem. And then I want you to notice the variables, because we have to come up with those variables that are around it. Well, the variable to the left is going to be the area of the rectangle. So we're going to put area of a rectangle on the left. And then on the right, we always have k. I don't know what my constant is yet. They haven't told me. But then I need to come up with my other variable. Well, what's the variable to the right of varies directly? The length. So let's go ahead and do k times the length. So that varies directly does a nice job of splitting up our equation. So you can in fact just take whatever variable is on the left, plug it into the left, whatever variable is on the right, plug it into the right, and then you just have your k that you drop down. Now we can go ahead and use the information in the next sentence to figure out what is my k, because that's what we really want to know in variation problems are. What's my k? I need to know what my constant is so I can use it to find another area. So if the area is 50 square meters, then the length is 10 meters, okay? So let's plug in what we know. I know my area is 50 square meters. I don't know what my k is yet, but I know my length is 10. Well, we can go ahead and solve this for k by dividing both sides by 10. This gives you k equals 5. So I now know that my k is 5. I can plug it back into this formula. Let's plug it back in so it becomes the area is equal to 5 times the length. And I now have the formula that this rectangle holds. So now the final sentence is find the area when the length is 25 meters. So now they want me to find the area, and I know the length is 25 meters. So let's go ahead and plug in what I know. I know the length is 25. I also know my k is 5. that means my area is going to be 125. Now, I know this is area. Area is meters squared or square meters. Okay, so that's just my units that I want to plop on there. Now, be very careful when you're doing these that you first always find K, plug it back in, and then you're allowed to find your second problem. So just be careful with that. Okay, now let's look at direct variation as it applies to a graph. So in this problem, it says the graph represents the distance traveled varying directly with time. What would be the distance traveled after 8 hours? So hopefully you all picked up on that very important phrasing, varying directly. Did you all pick up on that? Hopefully. So whenever it says varying directly, you want to use that direct variation formula, y equals k times x. And what we need to do is we need to fill out this formula and figure out what's my y and what's my x. So what's to the left of varying directly? Well, the distance would be on the left of that phrase. So we would say distance is equal to k, because remember we don't know what k is, that's our constant, times x. And x is whatever's to the right, so the right would be time. You can also fill these out using your graph here, right? This is your x-axis, the horizontal is always your x, and the vertical is always your y. So you see x is t and y is d, so it does coincide. Okay, now we weren't given a specific point in our problem, but if you notice there are points on here. Let's go ahead and use this point. This point would be 5. After 5 hours, the distance he traveled would be 300, right? Okay, so we can use that point on our graph. Let's plug it in. So distance would be 300. Time would be 5. Well, let's solve for k, because remember that's always our first step. We want to figure out what the constant is. So divide both sides by 5. K equals, I believe that's 60. 30 divided by 5 is 6. Yes, okay. So it is 60. He's going 60 miles per hour. Now we can go ahead and plug that back in. So we now have distance equals 60 times t. So let's go back to our final question. What would be the distance traveled after 8 hours? So if you notice on the graph, we don't have 8 hours on here, right? We go up to what, 7? I don't know what 8 is, okay? But I can plug it into this formula to help me figure it out. So distance equals 60 times 8. Well, that's going to go ahead and be 480 miles. Always use those units, right? Okay, so this distance is in miles, so let's go ahead and use it. And let's double check that that makes sense for our problem here. So you see this would be 6, this would be 7, right? Let's go ahead and say this is going to be 8. Okay, so if I scroll up, kind of try to make a straight line, not great, but if we keep drawing, it looks that, yep, it would be about 480 if I wasn't so horrible at drawing straight lines. And you can see it's right under 500. So yeah, 480 miles makes sense. Okay, let's go ahead and move on. We are now at inverse variation. So inverse variation is going to be your second variation type, okay? There's only 3. And I think I almost held up 4 fingers there, but there's only 3. So inverse variation is where the value of one variable increases as the other variable decreases. So direct variation, both were going up. But inverse variation says, how about instead of both, they're going opposite. So one's going up, and that's forcing the other to go down, or vice versa, okay? So here's how the formula looks. Now you can see y equals k time divided by x. So now your constant is still on the top, but now you're dividing by that second variable. So now we have a division sign. Let's go ahead and look at see how that applies to an example problem. So Megan is drawing rectangles that have the same area. The length of each rectangle varies inversely with the height. And as I read that sentence, I should say, ooh, it doesn't say varies directly. It says varies inversely. So that means I need to use this inverse variation formula right here that I've so kindly given you, right? Okay. And notice that it says the length of each rectangle varies inversely with the height. So let's go ahead and figure out those variables. Well, what's to the left of varies inversely? That would be the length. So the length is going to vary inversely. So notice I put that on the left, and k is always on the top, and we're dividing by our second variable, which is whatever's to the right. Well, what's to the right? The height. So I've got my formula, and now I need to figure out what are the possible measurements of the length and width of a second rectangle if the first rectangle's length is 10 and its height is 7. So here's what we know. We know the first rectangle's length is 10 and its height is 7. Can we use that to find k? Well, yeah, sure. Let's go ahead and plug it in. So the length is 10. The height is 7. Well, sure, we can go ahead and find k. Now, remember, when I have a division by a number, and I'm trying to isolate that variable, to undo it, I just do the opposite of division, which is multiplication. What you do to one side, you got to do to the other. So this gives me k equals 7 times 10 is 70. So my formula is going to be the length equals 70 divided by the height. So that's going to be my handy formula for this problem. Now, it says, what are the possible measurements of the length and width of a second rectangle? So they don't actually give me a specific height or a specific length to come up with a second rectangle. But I can go ahead and plug in some values. You can pick any value you want. Try this problem with a couple different values. For me, I'm going to go ahead and let's say I've already done a height of 7. Why don't I do a height of 5? Sure, why not? No big deal. Okay, so if I make the height 5, that's going to say what for the length? Well, let's plug it into our formula and see. That means the length would be 70 divided by 5, which gives me 14. And if we want to, oh, there's no units on here, so I could just write units. Whatever the units are. So that would be one example of a rectangle where the height is 5 and the length is 14. You could come up with another one, make the height 70. I don't care. Then the length would only be 1, really teeny tiny. So come up with a couple other ones. Try this problem out on your own. Last type of variation, guys. I know you're super excited. This is the third and final. It's called joint variation, and joint variation is where one variable depends on more than one other variable. So instead of just working with those 2 variables, we're going to have 3 or 4 or 5 variables. Honestly, we're probably just going to stick with at max 3, so don't get too freaked out. But basically, it's really similar to direct variation. The only thing is that the equation looks similar. The difference is that the other variables are going to be on the right. So you still have y equals k times x, but now we have this extra z variable going on. So just be careful when you're doing this formula that you put your variables in the right spot. Okay, so let's go ahead and do an example using joint variation. So the volume of a pyramid varies jointly. Oh, key words that we should circle and notice. I know I like to harass you guys about that. So the volume of a pyramid varies jointly as its height and the area of its base. So since we know that it's joint variation because of this phrasing, we can go ahead and plug in to this formula. So what's the variable on the left? Well, it's going to be volume. K is always K. And then we need to pick the other two variables that are being multiplied on the right-hand side. Well, as its height and the area of its base. So the height and the area. So let's do A for area, okay? So you see volume equals K times height times the area. We've got all three variables. Now we can go ahead and figure out what that K is, because that's always the first step, right? Always figuring out what that K is. Now, a pyramid with a height of 12 feet and a base with area of 23 square feet has a volume of 92 cubic feet. So that first sentence gives us all the information that we can plug into our formula to solve for K. So it says the height is 12, so I'm going to go ahead and plug 12 in for the height. What else do I know? I know the area is 23, so let's go ahead and plug that in. And I know the volume is 92. So I went ahead and plugged it in for the correct variables. Now let's go ahead and solve for K. So I'm going to go ahead and simplify the right-hand side. So 12 times 23 is 276. Okay. Then we can go ahead and divide both sides by 276. So what is K? 92 divided by 276. It looks to be 1/3. 1/3. So I can now plug that K right back in. Okay, so now my volume is 1/3 times my height times my area. And in fact, this is the formula for the volume of a pyramid. And if you don't know what a pyramid looks like, I can just draw it real quick. Try to use my skills here. Oh, it looks like a pyramid. Kind of make it three-dimensional, right? Okay. That does not look right. There's supposed to be. Anyways, you get the idea of a pyramid. I'm sure you've seen pyramids of Egypt, right? Okay. Hopefully everybody's seen the Mummy movie. If not, you should go watch it now. Okay, so let's go ahead and figure out the last final question. So it says, find the volume of a pyramid with a height of 17 and a base of 27. So let's go ahead and plug in these measurements for our height and our area. So volume equals 1/3 times my height was 17 and the area of the base was 27. So volume equals, well, let's just plug this into my calculator. 1/3 times 17 times 27. It's going to get me 153. Now, since I'm talking about volume, I'm talking about three-dimensional space. So I'm going to cube my units. So it's cubic feet, or you could write it as feet cubed. Both of these are the same thing, whatever you feel more comfortable with. But that's going to be your volume there. So go out, try your joints variation. Those are the three types of variation we have. Make sure you're good with telling the difference between the three. Direct variation is where they both go up. Inverse variation, going opposite directions. And then joint variation is where you have more than two variables. So continue working on those, and best of luck this week.